I think it's about time so we can get started. The first thing for working on this tutorial is you'll want to have the software that we're going to use and the tutorial materials themselves. So we're going to present from Jupyter Notebooks in this repository, this PyData / parallel tutorial on GitHub. So you can get started by cloning this repository, and then the dependencies and things that we're going to use. There's some things like HDF5 and pandas, and in the repository is a conda environment file. So if you install Anaconda or Miniconda, then you can install all the dependencies for this tutorial by running this command, which will install all the dependencies and create a conda environment. And then you can activate the environment with this source activate command on non-Windows and just activate on Windows. And there will be a couple examples where you can use Spark. Spark is big, so we didn't include it in the dependencies by default since we're on conference Wi-Fi. But if you want to use Spark, then you can install that in with an extra command. And then once you're in that environment and in this repository, you can start Jupyter Notebook server by typing Jupyter Notebook. And then we're going to start with some generated data that you can produce by running this prep.py script. So if we can get everybody started and so that they've got all the dependencies, and then get everybody started generating their initial data, which will take a couple of minutes. Then we can do a bit of talking first while everybody's got that underway. Is everybody all set with that? Either have everything or are in the process of doing it right now?
If you're not all set, you should wave your hands wildly.
So this tutorial is broken up into two parts. So I'll do the first part where we're going to be talking in general about high-level algorithms and interfaces that are useful in parallel computing that'll just run locally on your laptop. And then in the second part, we'll switch to some larger scale computing, and we have some computing resources available to you to use with some actual distributed clusters to explore some larger problems in the second half. Where'd you go? Oh, no, they weren't. So the first, the structure that we're gonna go with is starting to learn about some algorithms used commonly used in parallel computing, and how those can be applied to get parallel solution and distributed solutions to your data analysis. The first algorithm that we're going to explore is called MAP, and MAP is extremely common. It's implemented all over the place. There are even several implementations just in the Python standard library that assign work in different ways. And ultimately, MAP is given a sequence of inputs, one or more sequences of inputs, call a function on each item in that sequence, and then store or return the sequence of outputs that are the result of that computation. And so a use of MAP generally looks like you can write a local version where you just do a for loop and you iterate through a sequence and append those items to a list. Or in Python, there's a built-in function map that just does this algorithm locally. It's not parallel, but it's the algorithm of, given a sequence of inputs, give me a list that is the result of calling a given function on that sequence of outputs. And it's implemented all over the place. So pretty much every parallel computing framework will have an implementation of MAP that you can use with different advantages and disadvantages and extra controls for tuning how that work is assigned. So in general, a framework will provide MAP that, so we've got MAP, the local case where it's just doing that that locally, but a parallel computing framework such as Dask or IPython Parallel or Spark will distribute that work in some way. And map may be a method on some client object, or it may be a function. So the transition from local, if you can write your local code in terms of map and just run it locally, you can often parallelize that code simply by just saying, switching from using the Python built-in map to calling the map method provided by your parallel computing framework. And so now we're going to switch over into the repository. So we've got our Jupyter Notebook server running locally. And then in our repository, we've got a directory called notebooks, which is where our notebooks are that we're going to work with. And we're going to start with the first notebook called map. Yeah. Yeah, so is anybody not able to get things running locally? Okay. And so one of these folks can either help you deal with that if it's a small issue, or there is a cluster that already has all of these materials and all the dependencies that you can use if you can't get things installed. And that is at pycon-parallel.jovyan.org. And if you go to that URL, you should get a big blue button that says "Give me a cluster," and that will set you up with an environment to follow along with the tutorial. Yeah.
So hi everyone. Is this on?
Yeah.
Great. Hi everyone. My name is Matt. This is Min and Ben. And so the first part of the tutorial, we're going to run ideally on your local laptops. And this gives you a good sense of sort of how much power you can get out of your 4 or 8 cores on your laptop in a nice way. You're going to learn also a lot about parallel algorithms. So generally speaking, how do you what kinds of programming do you do to be parallel? And you can learn those well on your laptop, and they will apply well onto a cluster. In the second half of the course, we're going to work on a cluster. So there's a button you can press that will give you a cluster with about 32 cores that you can play with. Ideally, you're not using this until the second half. But if you need to, you can switch over now, and all the notebooks are there as well. So if things aren't set up for you right now, you can switch over early, and you'll be totally fine. But we'll get to play more with the cluster in the second half.
Yep. Okay, so we start by running our prep.py if you haven't done that already. This will be really quick. If you have run it, this just generates some random data to work with. And we're going to load, because we're interested, if we're doing parallel computing, that's often because we're interested in performance. We're interested in taking something that we know how to run and making it go faster, making it solve bigger problems that we can solve locally. And SnakeViz is a handy tool for doing profiling, visualization of performance profiling information in Python. And it works as an IPython extension. And we're going to load it here. And we'll see it momentarily. Just import some dependencies. And now we load, create our inputs. So remember, map takes a sequence of inputs that we're going to operate on. In this case, that sequence of inputs is a list of file names that contain data in JSON files. And then what we're going to do is we're going to just go through all of these JSON data files and then convert them to HDF5. And we're going to profile that with SnakeViz. This is going to take a little while. We're just doing it locally in serial. But you can see we're just, for each file in the file name list, do an operation on that file. And then when this is done, it's going to open up a new tab. And what we have is a visualization of the where Python spent its time in that operation. And we can see it spent a lot of the time in a list comprehension. There was some time, you can see the information shows up over here, where when I hover over something, We can see that we're actually spending a lot of time in this piece, which is JSON decoding. You can see the text that we're in the function decode in the JSON library. And then we can see we're also spending some time instantiating pandas data frames from the data. So those are the two places where we're spending our time mostly. And then we're spending a little piece of time in actually exporting the HDF5. So to do the same thing in parallel, just working locally, we've got this workload that we've established that says, given a list of inputs, for each input, do something, which we can represent as a list comprehension in Python, which is just say, call this function on X for each X in the sequence. Or in Python, because Python has this map function built into it, we can say, I want my results to be the list of items produced by mapping F onto my inputs. And if we can express it that way, then we can do it in parallel by getting the one of these executors from the standard library. So Python standard library has this module called concurrent futures that gives you an API on asynchronous execution. And the async APIs with futures and from concurrent futures is used by a number of parallel computing libraries in Python because the common interface that exposes these algorithms for remote or parallel execution. So in this case, because it's called process pool executor, it's spinning up a process. There is also a thread pool executor that spins up a thread. And which one to use will depend on what code you're running. So there's the process pool is more heavyweight in passing data across the boundary, and the thread pool, but the thread pool you're dealing with the GIL. So if each task releases the GIL, then you're generally better off using a thread pool. But if it's doing a lot of computation in Python, where it's holding or grabbing and releasing the GIL a lot, then you're better off using the process pool. So just for an example, what we want to do is a toy where we're just sleeping and then appending items to a list. We're using the time magic from my Python to see how long this is going to take. Well, I'm sleeping 8 times for 1 second. That takes about 8 seconds. I can do it in parallel. And for those on Windows, there are some issues with the process pool executor on Windows, but there's a library that does work on Windows. So you'll need, if you're on Windows, you can install Loki and then import process pool executor from Loki instead of concurrent futures. But otherwise, everything's the same. I can make this a little bigger. And so in this cell, we've defined our function, which is slow increment. Take a number and return that number plus 1, but take 1 second to do it. And so now we've created a process pool executor, which is an API around a collection of processes. And the default is to create 1 process per core on your machine. So I'm running a 4-core laptop. When I create a process pool executor, it will create an executor with 4 workers. You can pass a number explicitly to say, give me 2 workers, give me a dozen workers, but the default will be the number of cores on your machine. And here we're just calling map. This time it's the map method on the executor object and passing that back to results. And so you can see this is 8 seconds of work that we're completing in 2 seconds because we're doing it on 4 workers in parallel. And so that's an example of taking a for loop and then turning it into a map and doing it in parallel. So now the exercise is, given our initial for loop of converting these JSON files into HDF5, can you do that in parallel with the process pool executor? Yes?
I have a question.
Sure.
What is the password to the Jovian website?
It is PyCon 2017.
Is there a space or a dash in that?
No. And it's all lowercase. So here we've got our for loop, which is iterate through the file names and convert them to HDF5. And now the assignment for you folks is, can you run the same code but in parallel with the process pool executor? And so when we're working with map, as we saw in the previous example, the first step is to take the body of your for loop and turn that into a function so that you've got something to pass to map. So if our inputs are file names, what you want is to turn that into turn the little block of code that you're doing for each file name into a function. Yes?
Is snake viz any good at multiprocessing? Because when after I do the map example, I'm spending all of my time in acquire on
Yeah, so you see this comment that says try replacing time with snake viz once you've got the parallel example. Let's, yeah, we'll get to that momentarily. So here's one solution. So we're creating our process pool executor. We've got our function that's load the JSON and then store it in HDF5. And then we just map load parse store onto file names. And we can time this and see how long this takes compared to the serial case. So this took about 5 seconds instead of 10 seconds. So that's twice. That took about half the time, and so it's not perfect, not a quarter of the time, because there's some contention on disk and things like that. But as was just mentioned, once you've got it working, you can, okay, now we've got it in parallel, let's see where we're spending our time. We can run snakeviz on this and see what, where does a profile say we're spending all of our time in this parallel workload. And it says we're spending all of our time in something called wait. And that's because the work is no longer local. And so when I'm profiling the current local thread, all the current local thread is doing is waiting for results from remote workers. So I don't have all of the profiling information from the remote tasks. And so this is one of the things about doing parallel computing is that profiling can often be very difficult. Because once the execution is distributed and remote, getting all the information about where everybody's spending their time can be quite tricky, because often the profiling tools only really work on local execution. And so that's why it's really important to optimize your individual tasks locally, where you have all that information available, and then optimize kind of the parallel algorithm separately. And if you recall from the first example, when we pulled up SnakeViz, we spent almost all of our time decoding JSON, so just reading those JSON files. And because of that, we can investigate and find out that there are actually a lot of JSON parsing libraries in Python with a wide variety of performance characteristics. And so if we import the library UJSON, which is a particularly fast JSON implementation, we can run the same example locally in serial, where we're just switching JSON.loads to UJSON.loads. And we can see that it's almost as fast running locally in one process as it is running in parallel in 4 processes, just by switching to a better JSON parsing library. And so the important takeaway here is that just switching to parallel isn't necessarily the best way to make everything run fast. That often optimizing your single task performance can get you as much or more than parallelizing your work. And then a bit of background. So we're mostly using concurrent features in the process pool executors, which are kind of the modern API for doing this local parallel computing. But before there was concurrent features, there was something called multiprocessing pool, which has a similar exposure of map that has something called represents results as something called an async result instead of a future. But the model is very similar, and then the API is just a tiny bit different. And we can see that we've got, from a pool instead of a process pool executor, we get the same kind of work. So we've seen SnakeViz for local profiling, got process pool executor for doing local parallel execution, and then noting that optimizing your individual tasks is often at least as important as parallelizing your work. So the next algorithm we're going to look at is called submit. So we did map, which is take a single function and a collection of inputs and call that function on all those inputs. Submit is like one piece of that. Not all computations can be expressed as run the same function on a whole bunch of inputs. Sometimes you're doing correlations or some operation on individual executions that you want to compose your computation in terms of a whole bunch of computations. Submit is like producing a single node in that map, where with submit you say, okay, I want to call this function. I've got a collection of outputs, and it's not a sequence. Maybe it's a dictionary with some structure, and each node in that computation should correspond to calling this function on these inputs. And what we want for that is submit takes that computation and says, okay, now instead of calling this function and storing it in the outputs, schedule a call of that function so that I have a reference to that result, if not instead of the result itself, and then I can fetch that result at a later time. And this lets you build a a graph of all of your computations without actually having to start computation immediately. And so here I've built, instead of a dictionary of outputs, I have a dictionary of futures. And those futures kind of are handles on outputs that haven't been computed yet, or may not have been computed yet. And then I have a last step of when I actually need my results, then I call the result method on those futures. And this lets you do unstructured computation, so you can assign individual tasks as appropriate and construct arbitrarily complex computations. And then when you're done building, just kind of building your schedule, then you can retrieve those tasks whenever you need them. So we can, for instance, look at something familiar. In this case, this is what map looks like. You can see map as getting a sequence, as applying submit to each, submitting a function on each argument and then collecting the results at the end. And your scheduler, see in this example, we're storing a bunch of outputs locally in a set, and we can do that in parallel by just storing the outputs as the futures corresponding to those results, and then when you're done, you retrieve each result when you need them. Yep. And back to the notebook. So we're starting this time with the HDF5 files that we produced in the previous notebook. And we're going to work with those. And so in this case, we've got a series is a dictionary keyed by file name, where the values are the close column of the table. And what we want to do is compute correlations between each of these sequences. So there's an array. Now, series is a dictionary of arrays keyed by some name. And what we want to do is compute pairwise correlations between all of those arrays. Oops. And so in this case, we're doing it in serial. So we're iterating through all the file names. And then we're iterating through all the other file names, so all the file names that are not the same, and then storing the correlation between those. And then we're getting the maximum item with the maximum correlation. And so we can plot two correlated series. The two series, either they're randomized time series data, stock type data. And this is plotting the pair of stocks that are most correlated with each other from our collection. And you can see that they have kind of somewhat similar shape with the peak in a similar place and so on. And so we start out with something that fits in a map well, which is just load all my data. So for each file name, load that data. But then for a more complicated structure that doesn't fit as well into a map, compute a data point with the two keys, the two names as the key, that correlates those two series. You can construct that as a map, but it takes a bit of work to produce the proper arguments to that map. It's certainly easier if you can to just schedule each individual computation with a single submit. So this is where submit comes in. We're going to, in this time, create a thread pool executor instead of a process pool executor. So we're running in one process with threads. And here again, we're using our slow add, where we sleep for some period of time, and then we return the sum of two arguments. And this time with submit returns a future. And so a lot of these parallel computing frameworks are based on this general asynchronous computing API structure of futures, where a future is a handle on a result that may or may not have been computed yet. And you can use these to potentially chain computation of schedule wait for the result and give it to me, or schedule another computation that should start when that result is available. And so, in general, the key method on a future is result, which will wait for the result of that computation if it hasn't been completed, and then when it's completed, return it. And so if we call submit many times, then we've got many many results. So in this case, I'm calling slow add locally. This is the serial case. This should take 10 seconds because I've got 10 tasks that each take 1 second. And this time we're creating, so it's the same arguments, but we're calling submit instead of calling the function directly. And then we have this extra gather the results task at the end. And this is our parallel map, and this takes 3 seconds instead of 10. Now, the nice thing about submit is that you can do more complicated things than map, and you don't have to cram everything into a single list somehow. So in this case, I've got I and j, and I'm computing the sometimes the addition, and sometimes the difference, sometimes the sum, sometimes the difference between two numbers in two ranges. And then what we want to do is, so given this computation, can you do that in parallel using just submit? So we've got each task is either slow add or slow sub. Can you do that in parallel by submitting each computation and then waiting for them at the end rather than doing everything in serial? Oh, sure. If you're sitting over there. So there is also a Gitter chat room for the repository we're teaching from. So if you're not familiar with Gitter, Gitter is a chat system that is associated with Git repositories. So you can go to gitter.im/pydata/parallel tutorial, and so you can hop in there and ask questions and help each other out if you want to jump in there and see and ask for help from Ben if he's sitting at his laptop. We'll be watching the chat, but also you can help each other in there, post solutions and things. Yes, question.
Hi, Min. I have a question.
Yes.
So let's say I didn't finish the last notebook. I think I'm probably gonna have to use the HDF5 files or produced there last time, but I didn't actually figure out how to do that. So how can I get the solutions from the last notebook to complete this one? Are the solutions available?
So in each notebook, for each exercise, there is one of these cells that says load from solutions. And that's just a Python script that implements a solution to that problem. So if you run, I guess I could spoil this one.
Maybe for the last notebook? So like if I...
Yeah, so if I can go to
How do I
the
solve
last
map?
notebook in the map, I can, well, I think I cleared it actually.
Undoing the cell.
Yeah. So this cell has load solution/map1. If I execute that, it will replace that cell with a solution. And this is in the repository already. And then you can execute that cell, and you've got the solution right there. So it is important to have executed the first notebook, which produces the HDF5 files that we're using in the second notebook. How are we doing with submit? Ready to see our solution on submit? I think so. Okay, so we've got our functions, slow add and slow sub. And we have the exact same for loop that we had before, except instead of appending items to our results, we've got a new intermediate structure that's our futures that has the same shape as the results. But each item in that list is actually a future instead of the result. And then we add this extra step of, okay, now that I've submitted all my tasks, and I'm ready to wait for the results. So gather those results and then and store them. Yeah. So the question is in terms of what's actually happening in terms of what's happening in parallel and what's happening locally serially. So I am serially going through and submitting all my tasks in serial locally, but submit is very fast because all submit is say executor, please compute this at some point. So I serially submit all of my tasks. But the actual computation, which is the slow part, is what's done in parallel in the background. And then the last step where I'm waiting for the results so this f.result call is what's going to wait for that result to finish and then return it. So this, if you look at the timing of this, I'll get to this line very quickly, which is I have submitted all my work to be done. And then I start waiting for all the results at the end. Yes?
Does f.result block until that particular future is done?
Yes, f.result waits for the result if it's not done and then returns it.
So it wouldn't just do all the fast ones first and wait for the slow one to go at the end? The slow one went first, it would just block and wait for that one first.
In this example, yes. There are other ways to iterate through a collection of results where you don't care about the order and you want to just yield the results that are as they're finished. And there are algorithms that do this. But in this case, the order is sensitive, so it waits for the first result. So even if the first result submitted could be the last one to finish, so the first f.result might wait a long time, but that can return, and then all the other ones will be very fast because they were computed and returned before the first one finished. Yes?
What's the difference with multiprocessing? Which one runs faster?
What's the difference with multiprocessing versus threading? So futures is really just an API for representing asynchronous computation. So I can use futures with multiprocessing and multi-threading, unless you meant the multiprocessing module, in which case I would have something called an async result instead of a future, which are ultimately just different ways to spell the same thing. There might be implementation details where one's slightly faster than the other, but it doesn't matter too much. So now you have another exercise that we've done, kind of our toy submit, back to the correlation that we started this notebook with. Of we want to compute pairwise correlations between all of our series. The question is, can you compute all of these correlations in parallel using submit? So each key in the dictionary should be the pair of file name A and file name B, and the value should be the correlation computed with pandas. So just like with map, the first step in something like this is define a function that you're going to use to compute each node. But unlike map, you're not going to take just one argument for every element. You might take two.
We're going through these notebooks quickly, a little bit time constraint. I suspect that no more than like half of you are finishing the map. If you want help, please wave your hands and ask us for help. Ben and I are kind of bored right now.
That's possible. Yeah, so the question is, you think thinks that he has the right answer, but it's not. It's actually slower than the serial case, and that's entirely possible and not uncommon at all when parallelizing things. That there is something that we will learn a bit about immediately after this, but there's something about picking threads and processes and having some understanding of what's involved in your tasks in order to pick an appropriate way to run them, where the overhead of doing it in parallel might be more costly than doing all those tasks in serial. And sometimes threads can be faster because there's less data movement, and sometimes they can be slower because there's contention on local resources. And we'll explore that specific example immediately after this. So if you're seeing interesting performance results, you might try running the same code with a process pool executor and a thread pool executor and compare the two. See which one's faster. Yeah.
Shouldn't parallelism always be faster?
So the question is that shouldn't parallelism always be faster? So the answer is, surprisingly, no. There is overhead involved in any parallel computation where you have to send the task to all of your workers, and that costs something. That you have to say, okay, here's my function and here's my data, send it to the worker, whether it's a thread or a process or even a remote machine, and then that does its computation, and then it has to get that result back. So there's overhead in the scheduling, and this is where different executors do scheduling in different ways and will have different overheads. And so you have to make sure that your tasks run in parallel. The overhead of doing that in parallel has to be less than what you're going to save by doing them concurrently. And that's just something that you have to have some understanding of your system and your tasks for whether that is going to help. And something specific to Python that makes threaded parallelism difficult. So when you've got multiple processes or remote machines, then the overhead of sending the data and getting results back to those workers is relatively high because it's sending it over the network or over pipes, and that takes a bit of time. If you're using threads, that's very, very quick because you're just sending pointers around. You're just saying, hey, call this function. You already have it in memory because your memory is the same as mine. But in Python, there's something called the global interpreter lock, or GIL, that means that only one piece of Python code can be running at a time. So Python has threads, but you have to be careful because multiple Python threads can actually only be working if the different threads are in what are called GIL releasing blocks of code. And numerical Python code, such as pandas and NumPy, are generally fairly careful about releasing the GIL as much as possible. But you have to have some understanding of whether your tasks release the GIL or not to know whether it's appropriate to be doing multiple of those tasks in threads in one process at the same time, or if you're just going to be switching, handing off the GIL and fighting over the GIL all the time.
There's one GIL per process, per core, basically?
One GIL per process. So you can be using all your cores in one process, as long as those are as long as that process has enough threads, and those threads are doing tasks that don't hold the GIL. So that can be a lot of NumPy operations, for example, don't hold the GIL. So if you're calling C matrix multiplication routines and stuff, that won't hold the GIL, and you can be doing that in multiple threads just fine. The same with I/O operations, like waiting for bytes on the network. So if your tasks are actually fetching data from the web, that generally won't hold the GIL either. I think we can load our solution. It looks very similar to the code before. It's just we've defined our correlation function. This time it takes 2 arguments instead of 1 like we did with map. Our 2 arrays, or our 2 pandas series. And then we're calling a.core b. And then instead of calling that directly, we're submitting that function. And this time we're doing it with a thread pool executor. Oh dear. If you saw that problem, I saw this one time out of like 100 yesterday. Let's see if I can. What you might see in your terminal is something that looks like this. BLAS, program is terminated because you tried to allocate too many memory regions. So this is a thread safety thing with underlying C libraries. If you're using OpenBLAS, if you're using MKL or something else, then you're probably okay. This seems to be a non-deterministic thing, so I can just load my file names again, since my process actually died catastrophically. Oh, I need to load my series. So I've got my series and my file names back. And then I can run it again. Yeah. And this time it was okay. And we can time it. Yeah, so this was a bit of a race condition in OpenBLAS that this is one of the things that happens with parallel computing sometimes. And so I ran it this time. And for me, this wasn't slower. This was a bit faster, but you might get different results. Yes?
Is there any particular reason why series isn't put off into the future? So like you pass in series of A?
I am passing in series.
Yeah, is there a reason? I mean, is there like a
Oh, so correlation, like,
yeah, so that you're not parallelizing that as well?
so the reason is that getting items out of a dictionary is very fast. So there's no real benefit. And another reason is that series is all of my data. So it's not a big deal now because I'm using threads. But if I passed series, that contains all of my series, which might be really huge. And if I'm doing it remotely, I have to pass those arguments actually over the network or something before they're computed. And it would be better, because moving that data can be costly, you want to only send the data that you actually need for the task. And so kind of continuing this, you can see, try to compare your results, performance results, with a thread pool versus a process pool. And see what we get. Is it going to be faster with processes or slower? It's going to fail. Oh, because I was in the middle of typing it wrong. So 4 seconds versus 400 milliseconds. So you do need to be careful. And so why do we get this result that it's so much slower with processes? Anybody have an idea? Yeah.
Because it has to ship the data across inter-process communications instead of just being able to share it.
Yes, that's exactly right. So it actually has to, because the task needs the data in order to compute, when you're running with processes, it actually has to take the data that's already in memory and then serialize it and send that to the processes, which then compute, deserialize it, do some computation, serialize the result, and then ship that back over the network. And that's quite costly when you've got large numerical data. And so there was a big advantage in using local threads, because when you're using threads, you don't have to serialize that data because you're just passing pointers in memory around. So it's nice when you've got libraries like pandas or NumPy and that do these operations that don't hold the GIL. It's really nice to be able to use threads when you can, because it's quite a bit quicker. And now here's an example where we can crash things on purpose. So this died because, so threads are nice and fast, but the HDF5 library that we're using is not thread safe. So I can't use HDF5 in threads like this because everything will die. So that's another thing that you might need to be aware of. So we've done sort of low-level operations of map takes functions and arguments, submit takes a function and arguments. The next kind of large, high-level notion is taking a high-level data structure that represents a potentially distributed a collection that knows how to do things in parallel. So this can include things like queries from databases or arrays or distributed collections of various sorts. And collections often provide an abstraction that says this is an object that represents a collection of data, but maybe it hasn't been loaded yet. Maybe it will never be loaded. And then you can call methods that essentially build up a schedule of computation, but it won't compute results, or it doesn't have to compute results until you actually ask for a particular value, and then it will only compute what it has to in order to get that value. And this lets you do operations on potentially very large data sets that don't fit in memory, but use APIs that are familiar, that look like lists, that look like arrays, etc. And you can perform those operations. And then this is using the asynchronous model of these futures and things, where you're scheduling that computation instead of actually performing it at each call. And then you, just like waiting for the result, you only actually start computing once you ask for a particular value. Yeah, I'll do that. Yeah. And then back to collections. So we've got two collections that we're gonna look at. I'll probably just cover one and then gloss over the other one a little bit. So the first one we're gonna talk about is a collection that's a high-level representation of something like a Python list or a JavaScript array. And there are two implementations of this notebook. So there's 3a, which implements it with Spark, and then there's 3b, which is the one that I'll go through that implements it with Dask. And both of these libraries have similar notions of a distributed collection of a distributed sequence, essentially. So in this case, we've got a sequence of data, and we want to, again, in this case, we've got a Python list, and then we want to turn that into this high-level representation of a collection. And we're going to use the library daskbag to do that. So we import daskbag, and this has a function from sequence that says, given a Python sequence, turn that into a daskbag. And you'll see that this is no longer a simple list. It's a wrapper, an abstraction around that list that has a notion of partitions and number of items. And then you can call compute, which is a method that says, okay, I represent now some computation on that data, and then you call compute to actually evaluate whatever computation has been scheduled and return the actual result. So collections like this have a map method. So just like you have a map function that takes a sequence, you can call a map method on a bag, and that returns a new bag that you can compute the result on. And there's also a filter method that, say, you pass it a function that returns a Boolean, and it will return a new bag with only the items for which that function returned true. And you can also do, there's a common operation when doing parallel computing is you've got a nested for loop of like computing, say, the areas of a bunch of rectangles. You want to iterate through all your widths and iterate through all your heights and then record the area of width times height. So that's a nested for loop. Sometimes you want to convert that nested for loop into a linear sequence for something like map. Taking those two sequences and producing all of the pairs in that nested for loop order is something called the Cartesian product. And so you'll see methods on Spark. I believe the method is Cartesian in Spark and product in Dask. And there's an itertools.product utility function in Python. And they compute the Cartesian product of two sequences. So in this case, we can take B and its Cartesian product with itself, and that gives you that for I in B, for J in B, every pair of that nested sequence. And you can, so each one of these methods returns a new Dask bag, and so that has all of the methods on that has all of those methods. So you can chain these operations. So I can say, given my initial bag, I can square it, and then that returns a new bag, and then I can take the product of the square with the original, and then I can filter that. So now I've got a bag where I've got two elements at each item, and I want to filter that where the first item is even, and then finally compute the result. There you can see we've got all of the items where the left item is even, and the even squares, and the right item is just going through in order. And so now we have an exercise. Can we do something that, yes, question?
I just missed, is Dask automatically sending threads out to the cores?
So Dask has, so what Dask gives you is this algorithm of building up these computations. And it builds a computation graph of what would you like me to compute, and then it submits that. And Dask has this concept of a scheduler, is that the right term? That says, okay, given a graph, assign that work somewhere. And Dask actually has a variety of schedulers, and I'm using local Dask right now. and it can work with local processes, local threads, totally in serial, or distributed processes across many machines. So it's Dask lets you choose how you want to assign that work, but the high-level representation of I'm composing this computation graph is independent of how I'm actually assigning that work on 2 nodes. So is using threads by default or just serial? Processes. Yeah. Yeah. So now we're going to. Yeah. So now we're going to do some parallel pairwise stuff, just like we did in the previous notebook, but we're going to do it with a high-level high-level Dask bag structure. So each item in series is we're loading the series just like we did before, and we're doing the pairwise correlations. And then to do it with Dask bag, we're going to start with, okay, I've got this list of file names. Can you turn, we turn that list of file names into a Dask bag, and now can you take that Dask bag and compute these all these pairwise items using the Dask bag methods. And these collection APIs are very powerful, but they do require thinking a bit in a bit of a different way. So with map and submit, you didn't have to think too differently than the code that you'd already written. It's like I write the same code, I just put in a little async computation, and then I wait later. With these higher level collection abstractions, we have some slightly new ways of thinking about how we assemble these computations, because we're building these collections, and each operation produces a new collection that only represents a scheduled computation that may or may not actually need to be computed by the end. So it requires a bit more of a new mental model than the lower level map and submit. This one requires a bit more thinking. This one? So this is a, for pandas series or NumPy arrays, when you do A equals B, instead of getting true or false, you get a new array where it's true or false for every item. Right, so this is what, if you do A equals B, you get a sequence of all of the equality. And so if you want actually the Boolean of does this entire array equal this other entire array, you need to get, are all of them true or false? So these outer for loops, that's our, where the nested for loop can be represented as a Cartesian product. So we've got the product of series and series. And then we want to filter. So exclude some of the values where a certain condition is true. And then we want to call a function based on those two values once we've got our product and our filter. And then we want to take the maximum value. Okay, ready for a solution? Or people still want to work? All right. So we've got our sequence, our bag from the initial list. We map the a function that loads the data. So our input is file names, and then we start with a map where we turn that bag of file names into a bag of series. And then here's our nested for loop, is that Cartesian product of series with itself. And then we want to filter and only take the items where the two values are not equal. And then we want to map. So for each remaining item, after we've done that filtering, we want to get the correlation of those two items. And then we want to take the maximum value. And then finally, we compute. So that took 7 seconds. The serial one took 2. And so why is that? Because the default scheduler for Dask bag is with processes. And so we've got that issue that we had with the previous example with submit. Sending those series, so I talked about Dask having this notion of scheduler, and there's multiple schedulers. There's local ones, there's in-process, there's multi-process, there's distributed. And the default for bag is processes, which means that we have the same problem that we had when we used processes in the previous notebook of each item needs to send that data, that series, which is expensive relative to the scale of task that we have. But the Dask has this notion of, so the core, so if we look at what core is, it's a representation. It's core.dask, is that right? Visualize? I don't have Graphis. So what this is a a graph of all the computation necessary to give me this value. I haven't actually done any work yet, but I have figured out what work needs to be done. And then I submit that graph to some scheduler to figure out, to actually get the result. And when I specify using Dask async, instead of doing it with processes, it's doing it locally. And again, I get back to 2 seconds. And just to compare Dask bag to PySpark to show that this is a common, a high level concept that's familiar. You can see this Spark context parallelized is the same as Dask from sequence. It has the same map method. It calls product Cartesian. When you've got 2 words for a thing, some people will use one word, some people will use the other one. And then the filter and map and max, and you can see that the Spark computation looks very, very similar to the Dask. So it's one way of thinking, but there are multiple implementations of that same way of thinking. So that once you're on top of Dask bag or Spark, it's easy to switch between one and the other. So I think there's one other collection notebook where instead of using Dask bag, I have Dask data frames. Feel free to look at that if you're particularly interested in data frames. It's the same kind of thing of building a high-level representation of operations on data frames that feels like a pandas data frame, but is actually partitioned and so that you can use it for either large-scale or parallel computations. And then we're going to finish with a bit of a capstone on these computations using scikit-learn to do a machine learning example using these tools for building our computation graph and distributing it in parallel. So I'm going to start with a few imports, and then we're going to do our serial example to kind of set the stage. And we're loading the scikit-learn digits data set and just displaying that. So digits data set is a collection of handwritten digits on these grids, 8x8 grids, used for training handwriting recognition or digit recognition and things. And some utilities that we're going to load that we're going to use just that do some of the work in this example. And with scikit-learn and machine learning in general, you often have some parameter space that you want to search. And so you've got a Cartesian product of, I want to use the C parameter and the gamma parameter and a tolerance, and I want to use those on some range. I know I want several values of this, several values of that, and I want to explore all combinations of these parameters. So you can see our parameter samples. This just samples, rather than taking the dense Cartesian product of all of these things, it samples different items from that dense collection. And for cross-validation, we want to take the data set, and it's something you do in machine learning of taking your data set and splitting it into your training set and your test set. And for cross-validation, often you take many different slices of training and test. And so we get our training set for training inputs and training outputs. And then we say for each test train split and for each parameter combination in all of our parameter search space, then we evaluate one item of our model for those parameters and that training data. And we see our results, and we've got this. So that's going to take a little while because it's doing a fair amount of computation. And then we can plot. So that took about 10 seconds, and we can plot our results. We can see our validation score of So we've got a 2D plot of two of our parameters, and then you can see the validation score, where higher is better. So we can see that the model does significantly better in this region than it does in all of these other areas. And then you use that to build your actual model, and then you can go and do your machine learning application. So this is often how one comes up with coming up with the parameters for a model. So the exercise, and this is a bit contrived because what we did was we very carefully set this up to say, okay, we're iterating through these splits, and then we're iterating through these parameter samples, and then we're computing one result by evaluating one item with our model, and then we're saving that result, and then we're plotting everything. And so now, can you take this computation where each data point for our machine learning model, where each data point, can we compute those data points in parallel? And there are a variety of solutions to this. You can use any combination of the tools we've learned so far. So you can put it together with submit, with map, with bag, whichever one you like best, or whichever one that you understand the least, and so you can learn more about by trying to do that one, or do all of the above. I thought it was 3 o'clock. I think it might be done a little bit early. And once you're happy with your work, you can turn up each of these parameters to get. So if you've got a really nice parallel setup that's going nice and quick, you can increase the number of samples and data points that you're going to use, and get a denser plot to get more information about the distribution of good parameters. How are people doing? Any questions? Anybody need help? Everybody? Yes? Oh, yeah, so the parameter sampler takes a parameter grid and a number of samples that you want to make. So now that you're doing it in parallel, you can turn up this 10 to say 20 data points to sample, or 20 samples, and then you'll get more dots on your graph. Now that you're making it fast. How many people are using map somewhere? How many people are using submit? How many people are using bag? How many people like what they chose? Right, so I think we can peek at one solution. So here's one using submit. We've got our thread pool executor. We're iterating. We've got our for loop just like the serial case, but we're using submit instead of calling it immediately. Add to the future, and then gather our results. See what we get. It's something very similar. And another result, this time with Spark. So this is like the Spark version is like bag. So we create our Spark context with 4 threads. Parallelize, this is the bag from sequence. We parallelize the parameters as well. Get our Cartesian product for the for loop. And then we map all of our, evaluate one data point, and then we've got our results. That took a while, though some of it might have been setting up the Spark context. And there's our validations. And now that we're in parallel, we can turn up the numbers, say compute 20 by 4 and do our parallel computation and plot it. And I've got a bit more detail that we've uncovered because we can afford to compute more points. Right, so just to summarize what we did in our first section, we learned about map, submit, and collections. Submit is very flexible. It's really distributed tools like Spark may not have something like this, but more generic tools like Dask or concurrent features or IPython Perl will have something like this. It's often quite easy to build something with submit, but maybe you're taking a lot of the burden of onto yourself and not letting the system try to do its clever things and understanding fancy algorithms and things. And then collections give you this high-level representation where you let the system do smart things about partitioning the graphs and distributing work, and they can help you. They often don't need that much input from you, but if you don't understand what they're doing, they can often you do have to understand a bit how they interpret the commands that you give it, because often those collections, making certain methods are a lot more expensive than others, and you have to be careful when working with those collections, because often you can shoot yourself in the foot a little bit with by causing too much communication and things. And then map is your simple case of I just need to do a lot of things. I need to do I've just got a whole bunch of inputs and I want to process them all. Map is the simplest way to do that, and it is available absolutely everywhere. So if you can phrase your problem in terms of map, you can compute it in just about any context. And that is our first segment on algorithms and high-level concepts, and we'll continue with doing things on a larger scale on a distributed cluster after a break. Any questions before we move on? Yes?
Can you talk a little bit more about the GIL and when the thread is processed? It's all seems to be wrapped together.
Next section. There's nothing after this. Oh, right, yeah.
I'm willing to wait if it's coming up next.
It is.
Okay.
But yeah, so there are these trade-offs that threads share memory, so passing data around is extremely inexpensive, but they also share things like the GIL that mean that Python operations, so things that modify the Python interpreter state, so like defining new variables, calling methods on Python objects, only one of those things can be happening at a time. And so in order for your work to be performant, to actually be parallelizable in threads, each task has to be spending a significant fraction of its time not holding the GIL. And that's often a very difficult thing to know ahead of time. What's a good heuristic for are you releasing the GIL? It would be, are you spending all of your time in a single function call, say a method on a pandas object or a method on a NumPy array? Most of those will actually be low-level C methods that release the GIL. But if your code is a whole bunch of Python code, then you're probably holding, and each one of those pieces is a small fraction of your time, then you're going to be holding the GIL for most of that computation, and then your threads are just going to be fighting with each other. But it's not unless you understand kind of the tools that you're using in an individual task, it's hard to say. But thanks to things like process pool executor and thread pool executor, it's quite easy. You just change thread to process and see which one goes faster. No. Plenty, yeah. We did it today. So things like NumPy and pandas will do CPU-bound tasks like matrix multiply or array operations. Those are CPU-bound tasks, but they do not hold the GIL because they're operations on C arrays that very carefully release the GIL and then go into internal C operations and then grab the GIL when they're done. Yeah, and because it's modifying only internal array state of a single object and not talking to multiple Python objects. So they're some NumPy and pandas operations are very GIL heavy because they're modifying things. You do need to be careful there. Yes. Yeah, so the question is, will you be using all of your physical cores if you're using threads and NumPy or pandas? Yeah, you can use all your cores. You can even, you again have to be a little bit careful because sometimes some of those operations will be linear algebra operations that use BLOS, MKL, or OpenBLOS or something. And sometimes those libraries are themselves multi-threaded. So you can end up saying, I've got 4 CPUs, I've got 4 threads, they're all doing GIL releasing NumPy operations, but each one of those is doing multi-threaded BLOS on 4 threads. So I've actually launched 16 threads of computation, and then you'll end up fighting, because you've got too many threads, you'll end up fighting with concurrency again. So you do have to understand something about what each task is doing, because sometimes that will be multi-threaded at the C level, even within a given Python thread. Yes, in the back. Yes. How do you start a cluster? So, on the break, when you come back, we're going to be starting doing computing on a remote cluster. So you're going to go to pycon-parallel.jovian.org, and you're going to click the big blue button, and that will give you a cluster eventually. And it'll wait for your cluster to start, and then when your cluster starts, it will redirect you, and you'll get a little login page, and the password for that is PyCon 2017. PyCon-parallel.jovian. Not this one. It's not this one. PyCon-parallel. Yeah. Oh, good. JOVYAN. Yeah, there's a link in the getter. PyCon, all lowercase, 2017. No space, no punctuation.
We good to go? Great. Hi, everyone. My name is Matt. As a first disclaimer, I speak way more quickly than Min. I'm going to try really hard to rein it in a little bit, but sometimes I speak really fast like this. So if I'm not being intelligible, please wave your hands, and I'll try to slow down a little bit. We're going to work on now. So in the last section, we learned about parallel computing, not about any particular library, but we learned about how to think about parallel computing problems in general, when you should use map, when you can use a big collection like Spark, or when you can use something a bit more flexible like futures, something a bit more sort of task-oriented. We did all that on a single machine, and all of those programming paradigms work well on a single machine. They also work well on a cluster. So we sort of learned how to program in parallel, and now we're going to learn how to execute parallel programs on larger systems. The short answer is that you probably know everything you need to know to do that. And now we're going to sort of start thinking about performance costs and some more complexity that arises when you have many different machines. So we left off with Min talking about the difference between threads and processes. I want to reiterate, because it came up a couple times. If you are using Python and you're using sort of the NumPy, Pandas, scikit-learn stack, you can saturate all of your cores in your laptop using only threads. You don't need to use processes. The GIL is not a problem for the scientific Python stack, the PyData stack. It really isn't an issue. That being said, sometimes you want more than the 4 cores in your laptop or the 20 cores in your workstation. You want multiple machines. And so here we have many different processes on different computers, each of which has a lot of threads, and we can use many cores. So if you haven't already, you should go to, again, this page. When you click on that page, you get access to this button. This is a very satisfying button to push. And what this is doing, thanks to the good work of Ben in the corner and Min in the back, this is launching for you a cluster with about 32 cores. It's about 32 sort of single core machines. So all of you have a cluster of your own you can now work on and get a bit more power than you had just with your laptop. Is that spinning? I'm going to try that again. I'm working from Min's computer, so I apologize if it takes me a little to go. Maybe launching many clusters here. There we go. Great. Okay. You should see this page, and eventually it should turn into a Jupyter notebook. Show of hands, who has gotten to this page already? Okay. Has anyone not been able to get to this page? Okay, one person. Great. And password again is PyCon 2017. So in here, you'll find the familiar notebooks. We're going to start with the same example you did at the last section, but now we're going to switch to distributed systems. Before we do that, so we have running on this cluster. This is going to annoy me. We have 2 different systems. We have Spark running, and we have Dask running. You can see here we've got access to 32 different cores. At various sections in this class, we'll also want to access. Ooh, this is going to be tricky. Min, I need your help for a moment, if you don't mind. Can you split those? Or I want 2 things side by side. Yeah. Okay, so we're going to do the same exercise we did in the last section, but now with the distributed computer. As a disclaimer, so I work on Dask. I feel a little bad about this. The Spark stuff is not running as efficiently as it should be. Something happened weird yesterday, and the configurations are a bit weird. If you run Spark and things are slow, it is not Spark's fault. It is our fault. Yeah, that's perfect. So just to sort of give a little bit of satisfaction here. So we can use systems like concurrent futures or bags or data frames or RDDs, but now in a much larger system. What's going on here? Or not. Nope. Okay. Okay, thank you. Okay, so the wireless may be weird. And so we can still use our same interfaces like concurrent futures or bags or whatever, but those interfaces now all work on a cluster. So again, we're using the same tools you learned in the last section, but we're applying them now to a larger ecosystem.
So what's running on each one of the worker nodes? Is there a Dask?
Yeah, so each of the worker nodes has both a Dask worker running and a standalone Spark slave running. It's okay. Okay. I'm sorry. It's I'm learning to use someone else's computer here. So let's. Okay. So all of these systems, how they operate is that there is a single centralized scheduler with many different workers. So we, in our notebook, are submitting computations to sort of a head node into the cluster. That head node, that sort of scheduler, is distributing that work across many machines in that cluster. There are, however, some extra problems. So just as we sort of experienced with threads and processes, that there were some challenges. Some, one might perform better than the other. There's some extra challenges now. We need to move data not within the same machine, but across the network to a different machine. In order to do that, we always need to serialize data, and we need to then move it across a wire. So when we have objects that we need to move across a wire, we turn them into bytes. And there are libraries like Pickle that can help us do this. And we might compress them, we might move them around, and there are various trade-offs to sort of the kinds of things we're moving around. As you sort of get more used to dealing with distributed systems, these come up more and more often. Additionally, there are objects that we can't move around, things like locks or files that are tricky to cross sort of over the network. Additionally, we're sort of expecting, all these systems will expect that our software environment is the same. So they're expecting to have the same version of NumPy everywhere, the same version of Pandas everywhere. These are some of the extra challenges you get when running a distributed system. In this tutorial, we've handled all of those things for you. And so we're going to look again at our previous notebook. So in our previous notebook, in our exercise, we were looking at scikit-learn computation. And we had an estimator and some data. We were iterating over some training and testing splits. And we had some parameters for that estimator. And we're trying to figure out what were the right parameters that would give us a good result. So we're using some scikit-learn machinery. That machinery has some extra inputs that we need to decide. Based on those inputs, the scikit-learn thing will work well or will work poorly. On our local machine, we ran this. And it took a little bit of time. And we got out this nice plot. After a little bit of time, we got this nice plot that there's sort of a region where things looked good. So in this case, yellow is good and purple is bad. And we sampled a few points in here, and we got to see that, okay, maybe the lower right is a little bit better than the rest of the thing. But we'd like to get more insight. We'd like to know where exactly in that region of parameter space makes our scikit-learn models work well. And so we had solutions from the last section, like this solution with concurrent futures, that ran faster, but now we can replace, instead of concurrent futures submit model, we can replace that with some other distributed library that implements this same API. So there's libraries like Scoop implement this, IPython Parallel implements this, Dask implements this. These are all distributed versions of the same API. So instead of running this with futures, with concurrent futures, I'm going to copy over the same oops. I'm going to copy over the same cell that I had from our distributed services notebook, which teaches me how to connect out to my local cluster. So now rather than running with a thread pool, I now run with a distributed cluster. Nope. From that experience, we can then scale out. Sorry, I'm going to switch, because the web stuff isn't working a little bit, I'm going to switch to something slightly different, just so we can get some more rapid progress. Oh, that's actually really interesting to know. Thank you. I will switch after this to my laptop, where I think things will run a bit more smoothly. Okay, so once we have a distributed cluster, we can start to scale things up a little bit. And we can run these things more quickly. So here I just ran 100 or 200 of these computations in the time that it used to take us to run about 5. And then our image can increase in visual appeal. We can start to get more of a sense for what we're trying to do. So I'm going to switch my laptop out. In the meantime, play with this and try to see how you can get that thing to look more and more resolved by increasing the number of parameters.
Can you scroll back to show that progress line? How you enable the progress bar?
Yep. I'm going to cut out the thing. Sorry. We're going to stay with HDMI, so you should be hopefully no difference with you. Yeah. Sorry for fuddling, Min. Great, let's switch out of there. Yeah. It's still weird. Let's get better. Okay. Okay, so for some of the notebooks coming up, we'll be thinking about the kinds of things that can happen in distributed computing that can slow you down, or that can speed you up, depending. For some of these, we'll use Spark. For some of these, we'll use Dask. I tend to be a little more just familiar with Dask, and Dask has sort of some nice diagnostic plots, so we might focus on that a little bit more, but the ideas are very general. They apply to all cases. If you want this sort of setup with this page, you can go to Dask's diagnostic dashboard, this plot here. I recommend setting up your notebook on half of your screen and your web page on the other half. This can show you a little bit about what's happening on your cluster. This can help us to identify some performance problems. So here I ran not 10 or 20 of these parameters, I ran 1,000. And you can see here, this is showing for all of my 32 cores on my cluster, what they were doing over any particular time. They were calling this evaluate1 function. You see that my workers were sort of well saturated. They were pretty busy during that entire period. Now with those results, I now have a much richer picture of that parameter space. I see that there is some region down here where scikit-learn in this support vector classifier works very, very well. There's a region outside of that parameter space which doesn't work well. So if I just naively choose certain parameters, my scikit-learn code may run well or it may run very poorly. And this helps us to understand which parameters make it run well. We were able to get this nice picture because we had a cluster that we could parallelize over. Additionally, we could do the same thing with Spark, but now rather than running this locally, so Min ran this code locally on his laptop, now instead we're going to look back at the distributed services notebook, and we see that instead of running locally, we can now instead connect to a remote cluster. So Spark makes it very, very easy to switch from local execution to distributed execution. And it'll go ahead and do the same thing that happened before, but now using all of our workers. Okay. I'm not going to wait for that to finish, but this is sort of generally speaking the kind of thing we're going to do. We're going to do the same exercises before, but now we're going to scale out. When we're using Dask things, we're going to use this dashboard to help us understand performance costs. Okay. Ben, did you want to do group by sorting things, or should I do that? Okay. Sorry? So you're saying that if I run Spark context in one notebook, I should shut it down before opening up another notebook with Spark. Okay, was that the problem you were having before? Is that different? Okay, great. So Ben has just told me that it is challenging to have two Spark contexts running inside the same machine, apparently. So I'm going to restart this notebook before moving on. Otherwise, I'll have some performance problems. So we're not going to teach you sort of all the API of Spark or all the API of Dask. We're going to teach you some pitfalls. I want to bring up two interesting cases where we might write using sort of the Spark or the Dask API naively, and that might not be the right choice. There's often some other alternative algorithms we might choose instead. So we might consider that we have some random data, maybe just a bunch of random numbers spread across our cluster. We want to find the largest numbers. So maybe this is all of the students across the world. We want to find the best students. Okay. So naively, so here I'm going to construct a million random numbers across my cluster. And naively, I might implement this computation by saying sort all of my students, sort all of my numbers, and then just pick off the top 10 or the top 20. And this operation can be actually quite slow because sorting in a distributed context ends up being much more expensive than it was on a single machine. So some of our operations, even though they have the same names, now cost very different amounts. Great. So here I'm going to do the same thing twice. I'm going to find the top million elements. So here I've got this large RDD, this large collection of a million numbers spread across a cluster. And right now, all the numbers are just sort of randomly applied. I'm going to sort them and then take the top 5. It's going to take some time. Okay, it's taking more time than I was expecting. There we go. So we sorted all the numbers, and we've taken the top 5. When we find that the top numbers are indeed sort of pretty large, or sort of near 1. There's just a uniform bunch of numbers. Instead, we might run a different operation, which gives us the exact same results in much, much less time. And so the point here is that you may be running operations, and Spark may give you some API that seems very reasonable, but is actually quite slow. And sometimes you need to look a little bit more closely at the kinds of API that's made available to you. As another sort of example, we have some nice GitHub data. This is still much slower than it should be. I'm not sure what's going on, but yeah. Here's some GitHub data. So you have a cluster now, and you have access to a bunch of JSON data. And that JSON data, we can map a function over that JSON data, JSON loads, which just parses that JSON data into normal Python objects, dictionaries and lists and numbers and strings. Now we can sort of do some fun things with that data. We might take JSON, let's map. So this is all of the activity on GitHub for a particular day and maybe in a particular hour. And we can see that this first element, this person, David J. Husa, pushed some code to GitHub with various content and various times. Now we can do some fun queries on this data using Spark in our cluster. One thing we might do is we might want to find out how many of each push event how many of each type of event were there. Were there push events? Were there poll events? Were there issue comments? Were there making a new repositories, etc.? We can do that in a few different ways. So Spark gives us a couple of tools. It gives us a group by tool, so we can group all of our all of our events by the type. Then we can count all of those groups. This, however, tends to be a little bit slow. So this is the same API you learned with min. So we're grouping by. So we're grouping by this type keyword. We're then gonna map and count things up. What this did, though, is this moved all of the records of type issues or public event. They went to different computers, probably. Then each computer summed up all of those numbers. But this data movement ends up being actually fairly expensive. We could have also done this a different way, using more complex API with the combine by key operation result. Which gives us, again, the exact same result, but in much, much less time. There's a lot of code up here that you're not really expected to get immediately, and that's fine. I'm just going to talk at you for a brief period, and then we'll get to some more exercises in a moment. So the example of what's happening here is that let's imagine that we had a school, and I'm going to use sort of I'm assuming there's only men and women in the world, and I apologize for that. But let's say we had a school and count the number of boys and girls that were in that school. We had two options. One, we asked all of the boys to go to one side of the school, all the girls to the other side of the school, then we could count them. That's sort of what group by and then map is doing. Or, alternatively, we might ask each classroom, maybe each of these classrooms is one of our different computers, we ask each classroom to count the number of boys, number of girls in that classroom, and then send only one student to some central place with those counts, and we can add up those counts. And so in this way, we're minimizing a lot of data transfer, and things will work a little bit more smoothly. Sorry, this is making sense? Can I get a thumbs up, move on, be faster? A thumbs down, I'm sort of lost, please go slower. Or a thumbs in the middle, go, you're just fine. Okay, I'm just gonna move on. Look at data frames. Data frames are fun. Okay, so we have in the data frames notebook, so this is notebook 9, you have access to a bunch of data on S3. This is the New York City taxicab data set. It's stored in CSV files, 12 CSV files, totals about 20 gigabytes on disk, about 60 gigabytes in RAM. This is too much to fit on a single machine. We can look at a little bit of the data using pandas by just reading a few rows. Okay. But we'd like to read all of the data at once. So instead, we're going to connect to our cluster, and we're going to use, just like how we use Dask bag, which is sort of like a list, we're going to use Dask data frame, which is sort of like a pandas data frame, but it's split. It has many different pandas data frames across a cluster. But it has sort of the same API. So I think you'll enjoy this. This is fun. So we're constructing that Dask data frame, and we're asking our cluster now to compute that. And what that's doing is that it's reading a bunch of data from S3, which takes a few seconds, and it calls the pandas read CSV function on all of those blocks of bytes. And we get out an object, this Dask data frame, which has the same API as pandas, but now operates by telling many different data frames of what to do. Sometimes S3 can be fairly slow, especially when we're calling it from Google. So we might, look at df.head or ask for the length of that data frame. We call for the length of that data frame. Dask is going to go ahead and compute it for us. And how it did that is it computed the lengths of all the individual pandas data frames, sent all those individual results to one machine, and then added them up. And so now we can do normal pandas-like operations and get out nice intuitive results. So you guys now have access to a 60 gigabyte data set if you want, or a smaller data set. And you can start playing with some of these exercises. Who in the room knows pandas decently well? Nobody. 2 people. Who doesn't know pandas at all well? Ah, okay, this is interesting. I usually give talks at conferences where pandas sort of the norm. Okay, so hopefully some of this syntax looks somewhat familiar, somewhat simple. I pick out a few columns. I'm going to persist this, telling Dash to please trigger that computation for us. I'll give this a data frame which is smaller and has only positive pairs. So you can play around a little bit with the Dask data frame API. If you haven't seen this before, you might also want to look at the pandas API. So you can go to the Dask API, daskabeta.org, go to data frame, and API. So it'll tell you some of the functions that you can use on data frames, which can let you sort of manipulate this high-level distributed collection in parallel across a cluster. So let's play a little bit with these exercises. If you need help, if you need Panda's help, please be vocal, and Min and Ben will walk around, also walk around, and we'll help you walk through some things. Let's do that for around 7 minutes. We'll start again at 3:50. Well, so if you want to work on the full data set, it's just read data from 1 month. You can also put a star right there. That'll give you the full data set, which will take a little bit longer, but will be, I think, maybe more fun. these just quickly, and we'll go back to exercises. So if you aren't familiar with pandas, it's nice to do something like df.head to get a sense of what you're doing, what you're working with. We see we have a data frame of many rows and many columns. It's kind of like an Excel spreadsheet. If I want to get a particular column, like let's say passenger count, I can just, it's an attribute on that data frame. By default, this will just give me some metadata about things. If I do head, I'll get actually a few of those actual rows. So the first 5 New York City cab rides have only 1 passenger in them, which is pretty common. Passenger, all these columns have methods on them as well, things like sum. By default, this is going to be a lazy computation. For it to actually compute, I need to call compute. It's just like with dask bag. It goes ahead and computes lots of things for us, and we find that there are roughly 240 million passengers that took a cab in the city of New York. We might also do something else like mean. And the average ride had about 1.6 passengers. A nice bit of API in pandas is the group by method. You can do many things with group by. So I'm going to take we'll take the data frame, we'll group by the passenger count column. Then we'll get the trip distance and then compute the mean. So of all my rides, I'm going to group by the passenger count, and then I'm going to take the mean of the trip distance column. We find that most rides had 1 passenger, as you'd expect. A lot of them had 2 passengers. I'm sorry, this is different. So single passenger rides tend to be pretty long. They're about 15 miles. This might be rides to the airport, for example. As you get more and more people in the cab, that seems to go less and less. Maybe there's a bunch of people going out to bars. So with this sort of pattern, you can ask lots of interesting complex questions with pandas or with Dask data frame. They have the same API. So I'm just showing you the pandas API. The only difference with Dask is your add.compute. Oh, sorry. In these plots, you're going to see what all of the workers are doing over time. When you see a colored box, it means that it was running some function. So some function is running on some work in our cluster for some period of time. This is measured usually in milliseconds. When you see red, that's communication between the different workers. Is that to sort of trade data back and forth. This is like in our example when we're grouping all of our students in our school. This is sending that runner from each classroom to different classrooms, telling each other how much information the others have. And so you can look that when we're computing this, actually we're not doing a very good job. There's a lot of white space here. There's a lot of time when our workers are idling. Or there's a lot of time when we're sending data rather than actually doing work. So most of the time, a lot of our cores are actually not doing much. We're not being as efficient as we could be. And so in the next notebook, we'll end up looking at a few different kinds of computations. We'll be looking at this plot here and seeing how the choices that we make affect how well we can saturate our cluster. So pandas has a very important concept of the index. So every row is labeled. You see this sort of incrementing number here on the left. And that label is very important. It allows us to easily select out rows of certain kinds. In this case, our sort of incrementing number isn't very useful. It's much more interesting to set an index with something like maybe the pickup time. What's doing this is sorting our data set by one particular column. It'll now be very easy to say, give me all of the rows that correspond to May 5th, or do rolling operations so that we know sort of all these sort of nice time series operations. Sorting is very hard. You're seeing the cluster work pretty hard right now to achieve that sort for us. There's a lot of white space, there's a lot of red, a lot of data transfer, and many little thousands of computations that are running. We're also seeing yeah, so the question is, the asterisk and Jupiter seems to be going way before we're finishing up over here. That's probably just the wireless is slow. And so Jupiter is getting a signal, and this is getting a signal, but there's a lot more sort of data flowing through this thing. So yeah, it's a good observation. We also notice up here that it's showing how many bytes are stored in all of our workers, and they're orange, which means we're sort of close to running out of RAM on all of our machines. But now all of our rows are now nicely sorted. This can help you do a lot more interesting computations like joins and group bys across date times. This group doesn't seem particularly excited about pandas things, so I'm going to sort of leave it at that. But if you sort of know pandas stuff, this is interesting. This is nice to you. Like Min's point sort of very early on in the notebooks, when we looked at the UJSON library, playing with JSON parsing, we found it was faster just to use the UJSON library rather than use parallelism. That's also often the case. Pandas can be 10, 100 times faster than just normal Python. So if you're in here because you want to know how to speed things up, maybe they actually shouldn't be in this tutorial. You should actually be in a pandas tutorial. That may be more effective. You should. Sorry? It doesn't exist this year. Oh, it doesn't exist. You should go to one of the PyData or SciPy conferences. All great conferences. But you should sort of think about how to make things faster on your single machine before moving on. Okay. I'm going to hand it off to Ben, I think, in a moment. We're going to talk a little bit about the cluster that we have and how it was set up.
Does that work? Okay. Actually, before I get started, I want to ask a few questions. So in the room, how many people here actively work on a cluster? Okay, and so are those things running kind of batch schedulers like SunGrid Engine or Slurm or something like that? Maybe MPI? What about things like Yarn or Mesos? Do those things sound familiar? Some people? Kubernetes or things like that? People? Okay. So actually, generally before, you've seen some problems actually of like hitting the complexity issues of when you move from a single machine to parallel machine. Generally, I think probably Min and Matt would agree, before you even go down the road of distributed computing, maybe just getting a bigger box, if that's an option, is a much better one. It's a lot simpler to do a lot of these things. AWS, I think, almost has terabyte RAM machines that are available. Get one of those before you kind of run into some of these problems. Like that often, in the way that UJSON has solved problems, just getting a bigger machine also solves a lot of those problems. And you won't even hit any of these other issues. But when you do go down the distributed computation route, or you don't have access to those larger machines, you generally have to think about some of these other kinds of problems, or somebody has thought about them on your behalf. So how do you take your work and deploy it? Do you need to think about you and your colleagues also running on the same cluster, so that's multi-tenancy? How do you make sure that in those multi-tenant environments you share resources appropriately? Those are those schedulers that I was sort of referencing before, the resource schedulers like Slurm or Yarn or Mesos. And then how do I make sure that the environment that I have on my laptop or wherever I'm running can be replicated throughout the cluster? So if you're in Java world, you don't really have to worry about this. There's not this problem of I have all my Python libraries here. How do I move them over there? Java can build this big, giant jar file. Python has this inherent problem where I can't really easily kind of push all of my libraries that I'm using and ship them around. But there's ways around that. Oh, thanks. So one way to deal with some of these environment issues for those of you that have run on clusters or experienced this pain before is, again, trying to go down the easy solution is something called NFS. People heard about that? Great. So NFS lets you take your home directory and mount it everywhere on every single node in the cluster. It's a very easy solution to solving that problem because anything you do locally will be replicated everywhere else there. So when you try to import NumPy, it imports NumPy on every node, or it can import NumPy on every node. You can also take your environment and ship it around by zipping everything up and calling out to some of these resource schedulers. If you're interested in that, I can talk to you more about it after the tutorial. You can also ship a spec of the environment. Spark does this, and Storm does this as well, where you can say, oh, I want my environment that looks like this, maybe some YAML spec. Go build that for me as part of the job. So take some Spark work and some Dask work, package it all up, and also include something that you want to pre-install before you even run any code. And then the last option that seems to be gaining popularity, especially in the last few years, is to use Docker. Are people familiar with Docker containerization? Okay, so like nearly everybody in the class. Great. So we're using Kubernetes. That's Kubernetes is a Go application that is a resource scheduler primarily targeted at Docker containers. So I have an image, I want to run lots of containers. Kubernetes lets me do that very easily. It lets me expose various ports and set up services. It seems to be a resource scheduler of choice, primarily targeted at Docker containers. So I think it does work with CoreOS or Rocket or whatever else is out there. Fortunately for us, we've got some sponsorship from Google to run this tutorial, so we should all thank Google for providing us with this. We're running on, I think each one of you has access to 16 nodes. On each node has around 2 gigs of RAM, or 2 gigs of two CPUs and 8 gigs of RAM. So you have roughly, 8 times 16? My head's, 128 gigs, each of you, which is great. And as you all saw, you just clicked a button and you got access to this cluster. That took a non-trivial amount of work from Min and I and other people. And when you go to your institutions, you can also kind of demand these things. They're not superhumanly difficult. They just take a little bit of effort. But you should go back to your institutions and say, I want a button. Build that. It's really not an unreasonable request at all. F5?
For refresh.
Function F5 or just?
Saying this refresh.
Okay, that was weird. Okay, so generally our setup looks like this. Here's our big blue button. This is actually just a web app that's running inside of Kubernetes. Inside of Kubernetes is also just another proxy app. You can also notice that they're sort of stacked. The web app is stacked. There's multiple replicas of this running. So if one of them goes down, you can just spin up another one. And Kubernetes is taking care of all the load balancing for me. The proxy is actually what is handling your interaction from your notebook to, from the new URL that you got to the running notebook. So we go from the proxy to the notebook, and then inside of this small namespaced area, this isolated area, is where we have the scheduler and all the workers running. So those 16 workers plus one head node. And each of you are completely isolated from everybody else's network traffic. You can't see or hear or try and tap into any of that, unless there's some weird underlying issues with Docker that we don't really care about. But yeah, it's actually it's a fairly straightforward setup, and actually most of the time, many people have built this exact same architecture. Actually, Min was probably Min and Jupyter folks were the first ones to kind of go down this route with a tool called Jupyter Hub. People are familiar with that, or if they're not, then you should go look at it. How they essentially make it possible to go launch Jupyter notebooks inside of any cluster. So very similar to this, you want to satisfy all your users and have them be able to get access to all the data, have a notebook that's isolated. Jupyter Hub can do those things. So there's both, actually, there's a lot of enterprise and open source tooling that are built on more or less the exact same stack as this. So it really is not unreasonable. Really trying to implore you, go back to your institutions, tell them, I want a big blue button, make that happen for me. It has to be blue. I don't know. It's blue, I think, probably because Google is blue, or was at one point. What? Oh, or if it's orange, yeah. Are there any questions about this? If not, we can chat later. I think I'm done. But I wanted just to show you a little bit about how all this kind of work is happening, the kinds of things that people have to think about on the back end, and the kind of demands that you as users can push onto these folks. These are totally reasonable requests to say, make this possible, make my life easier, especially because other people have already done a lot of the hard work. And again, there's open source tooling, and there's also enterprise tooling that does these exact things. Okay.
Okay, thank you. Actually, it's really interesting for me to see that the pandas question, who knows pandas, there was like 3 hands, and the who knows Docker question, there was a bunch of hands. When we've given this tutorial in the past, that those ratios have been completely reversed. So you may have misjudged who we're talking to. So yeah, so it's interesting sort of seeing the PyCon community versus other communities. It's neat that Python generally has this sort of disparate split. People who are sort of more familiar with, say, like the NumPy space versus the Django space. And my guess is that this room is probably mostly filled with sort of more Django-y people. Maybe not, I don't know. Okay, so the next notebook will be fun. So we've played with distributed data frames. We've had to have this nice data set. Now we're going to think about how to make it fast. And so it's one thing to know an API. That's where we focus on the first half of the class. And that's another thing to try to now understand the performance limitations of your system and how to tune your algorithms and your computations to make things run well. This can easily be a factor of 100, factor of 10. So what we're going to do is we have in this tuning notebook, we have the same data set. And I notice that I've sort of filled up all of my RAM over here. So I'm going to restart my client, which will just sort of nicely flush everything out. I'm going to do the same, or load the same data set again. Just a small bit of the data set, just one CSV file. Then we're going to do a couple of computations, and we're going to start playing with some parameters. So by default, Dask has split up this single CSV file into 32 different parts. Those 32 different parts are actually uniformly spread across my 32 different machines. But I might want to spread it more finely, have many more but smaller pandas data frames. So again, one Dask data frame has lots of pandas data frames in memory on all my different workers. And then Dask is just telling all those pandas data frames to do things for us. But I might want, rather than 32, I might want 1,000 that are all about 30 times smaller. Or I might want one big pandas data frame that's about 32 times larger. And that's a choice that I'm making here. And Dask has made some sensible default, but we might choose different things. So this is often called partition size. And the more partitions we add, it's good because we can get more parallelism. There's now more things that we can split up work and have more threads working at once. But it's bad because that adds overhead. So there's a balance here. So we're going to do a computation, which is a computation we did before. We're going to sum the number of passengers. We want to make this computation very, very fast. Maybe this is like something we're running inside of, when a user clicks a button on our web application, we're firing off this computation, it's coming back. And we want this to be within sort of nice human response time. And less than that sort of 200 millisecond limit. And so we might play with a couple of these parameters. There's 2 parameters we're going to play with. One is the number of partitions. This is how finely we're splitting our data. And the other is split every, which is, as we compute this passenger count sum, so we're counting up how many passengers are, we're going to each pandas data frame and asking it to compute how many passengers were in that particular day of data or that particular hour of data. Then we're going to sum all these things together. We can do that in a few ways. We can bring all of those intermediate sums to one machine and then sum them there, or we can sum them by groups. Maybe 10 pandas data frames get together and sum up to 10, and they get together and sum up again to 10. So just to show that a couple of times, here I've split into 1,000 different pieces. I'm going to sum, bring them all together in just one big communication. Or I might split every 2, so that now I'm doing sums, and then every pair of data frames is going to sort of come together. And so you see here, there's a lot more communication, many more very small communications. And so your challenge is to minimize this number. So we computed that, it took 1.9 seconds. So can you play with these 2 parameters and find values of those parameters which minimize that number? And in doing so, you can sort of watch this diagnostic over here and see if you can have that guide you to good numbers. So let's do that for a few minutes. Let's come back maybe at 4:20. Yeah. So the question is, can you define split every again? So when you have data frames that are made of many, many partitions, often we want to do like a simple MapReduce algorithm. We'll often do some computation on all of them. Let's say compute how many passengers in that one particular pandas data frame. Then you want to sort of sum all of those intermediate sums. So if you had 10 and 20 and 30, you want to add those all together up to 60. If you have many, many partitions, sometimes it's better to take some of those and sum them, and then sum those intermediate sums and sum them together, in sort of like a tree summation. Split every is the degree of splitting at every level of that tree. So when it's 1,000, it's just one sum of all the intermediates. When it's 2, we're taking every pair of pandas data frames, summing them up, and all of those pairs and summing them up, and all of those pairs and summing it up. So you have a very deep tree with a very small degree per node. Yeah, so the question is, does it make sense to always match number of partitions to the number of physical machines? Not always. As an example, yeah. What's going on here? Min, question for you? I've got an error thing in Jupyter Notebook. Is that just a wireless thing? Oh, no, it went away. My Jupyter Notebook just told me error. Never mind, I'll restart and hopefully, yeah, I'll just answer the question early. Sometimes it's nice to have more partitions than the number of cores you have, in case some of your computations take longer than others. So if you have some computations that take a large number of seconds, and some takes a small number, it's nice to have some extra work lying around, so the ones that are sort of lazy or idle can take on that extra work. So it's nice to have more partitions than there are cores usually. But as you add more partitions, there's also some more overhead. So there's a balance you have to do. And you're learning that balance now as you play with this computation. Yeah. I think, so I'm trying to think about both Dask and Spark at the moment. Spark does have some mechanism for dynamically allocating these things. In Dask, there are some operations where it is very convenient to change the number of partitions, like whenever you're setting an index or doing some sort of sort operation. And at that point, we will sort of look at your partitions and make intelligent decisions. But that's all optional. There have been various attempts to do this, and typically we find that problems are different enough that it's hard to be magical, and it's better to just like let the user take on that burden. So the example from before, when I actually load my data, query times from S3 vary widely, especially when you're on Google hardware. So that so all of these green blocks are actually reading the same amount of data, and some of them are taking 1.5 seconds, and some of them are taking 10 seconds. And so it'd be nicer if we actually had more partitions here, if we were more finely partitioned, because then we could fill in all of this dead space where some of our workers were being idle. So this is like, we have stragglers. These sort of very long computations are taking a long time, and all the rest of our cluster is just sort of waiting for them to finish. And by being more finely partitioned, we can improve the saturation of our work. Okay, so my current best speed is 2 seconds. Can anyone give me numbers for this value and this value which improve on that 2 seconds? 32 and 32, someone says. In fact, 2 people say. So we're using the default partitioning that came out originally, and then we're also just splitting just all in one go. So all of those intermediate sums are going to one machine. That ran in 128 milliseconds. You got faster in the back? 10. So anything above the number of partitions probably won't matter. So 10 or 10,000 probably won't. Well, let's see what happens. Oh, I didn't do this? Okay, thank you. Ooh, that's much faster. Yeah, so we by reducing the number of partitions, we're also able to reduce the overhead. Computing the sum isn't actually something that takes a whole lot of time. It actually doesn't make a whole lot of sense to parallelize computing the sum. We're sort of, that's, Pandas does this in the millisecond or two, or in, the actual sum computations are happening in 1.7 milliseconds. Okay, so no matter what library you use, Dask or Spark or anything, you'll run into this problem of how do I, or even just using concurrent futures. You need to sort of start thinking about how coarsely or how finely you should be batching your work. Similarly, if I'm submitting a task with concurrent futures and that task takes a microsecond, the time taken to submit that task is far larger. So we might instead, submit a task that does 1,000 microsecond long things. So this granularity of computation is something that's very important that you have to think about a lot. Another thing we often have to think about is communication between different workers. And the algorithms that we choose may require more or less communication. Communication is often far more costly in a distributed setting than on a single machine. I'm going to restart things just to sort of, again, clear away memory. And here, rather than using pandas, we're going to use a NumPy example. Who in the room has used a NumPy? Oh. Why don't you all use pandas? Okay, so NumPy is a n-dimensional array object. Dask array satisfies the NumPy API, but is now a bunch of NumPy arrays scattered around a cluster, and it's going to coordinate all those NumPy arrays for us. So here we are going to make a 10,000 by 10,000 array composed of a bunch of NumPy arrays, 100 NumPy arrays across our cluster. And we're going to do computation, which is a matrix multiply. Take x, or use this dot function, which is a matrix multiply, and multiply it by x transpose. So if you've studied linear algebra, this is something you've seen. I suspect that's not the common case. This is common in lots of machine learning algorithms or lots of algorithms generally. If I run this now, it's going to take a little bit of time. So I started with 800 megabytes of data. It's actually not that much. And Dask is now going to do this distributed matrix multiply across our cluster, and we're going to find that it's pretty inefficient. It's inefficient for two ways. One, there's lots of communication. Those are the red bars you're seeing. So red is communication. Two, it's using lots of intermediate space here. So we started out with an 800 megabyte data set, but Dask is needed to move around the same array to many different computers. So we're filling up RAM by moving the same array to many different machines. So this is going to take a while. We can change this. So our array was constructed as, we have 10,000 by 10,000 numbers, and that's composed of a 10 by 10 grid of 1,000 by 1,000 arrays. So we have 100 NumPy arrays. They're all arranged in a grid uniformly. We might choose to change that chunking. We might choose to have bigger NumPy arrays, maybe 2,000 by 2,000. Or we might change to make them short and fat or tall and skinny. And how we make those choices may affect how much communication we have to do and how much computation there is. So just as in the last computation, how we sort of played with a couple of parameters, now we get to have changed the chunking of our array. And that will affect our performance. So we can do this with the rechunk operation, which takes the shape of the NumPy arrays So if I change the shape to 500 by 500, then I now have a 20 by 20 grid of NumPy arrays. And now I can do the same operation, and it'll take more or less time. So this is the next exercise. How fast can you get this to be by changing the chunk size? And again, you can change it by increasing or decreasing the size, but also by changing the asymmetry. So let's do this maybe for the next 10 minutes. We'll stop at 4:35. Maybe that'll be close to the end. Let's stop at maybe 4:32. We'll stop in 7 minutes or so. So see how good you can do, and we'll try to find the right times. For computation to finish. So if you've chosen the wrong choice, it may take a while. You can always do client.restart, or you can interrupt your kernel if you're waiting on things. So I'll make a bad choice and then restart just to get myself out of a problem. Or you may want to choose to start with a smaller array, just so you can iterate more quickly. So if you're sort of playing around a lot, it might make sense to choose maybe a 1,000 by 1,000 array composed of NumPy arrays that are just 100 by 100 chunks. That might be a bit easier. Alternatively, if you are running something and it's taking a long time, you might choose to interrupt that by going to kernel and then interrupt, and then doing client.restart. And that will flush out all the current jobs. It will tear down all of your workers and then start them back up again. Probably. Okay. So we're going to finish up. Thank you guys for your attention and for your patience. So we've seen a few things. In the first half, we talked generally about parallel programs. We talked about the simple case of just mapping a function across lots of inputs. There's probably 90% of what people need to do. This is sort of the very, very common situation. We looked at common tools like concurrent futures and multiprocessing, about Dask and Spark. But we sort of tried to focus on general ideas of parallel computing, like mapping or big collections or sort of arbitrary asynchronous computations. And those are all nice sort of patterns to know about, nice paradigms to know about. When you run into a situation, you might say, this situation, I think probably like map might be a good fit for that. You look at what tools implement map, and you can go with those. So again, the goal here is not to have you thinking about how to use concurrent futures. The goal is to have you thinking about the various options available to you and how to think about them well. We then sort of looked at playing with the cluster. We saw some difficulties, ranging from connecting to wireless to looking at communication and serialization costs and overhead. And these will show up no matter what tools you use. If you use Spark or Storm or Flink or Dask or MapReduce, thinking about overheads and communication, realizing those are now part of what you now need to start thinking about is of value. Again, so we are Min, who's Min RK, who works on Jupyter, myself, Matt and Rocklin, who works on Dask, and Ben, who works on deploying clustery things. And we want to thank the conference organizers, our various employers, and Google for donating credits. If there's any questions, that'd be a good time. I'm happy to stick around for a while. We're probably all happy to stick around for a while. But if you want to head out, you can head out whenever. Actually, let's take an official break now. So if you want to head out, and then we'll stick around for questions. So thank you all for your time.